Hello everybody, my name is Camille, and I'm here to guide you through some basic electronics. Of course, I'm one of your TAs for the semester this year for Chem 327, and I'm going to be, hopefully, an abundance of help for you when it comes to building and designing your own electronics sensors and tools. Naturally, you're going to want to be doing some sort of design or experimental design, and oftentimes you'll find that you don't have access to the tools that you need in order to measure the wavelength of light or determine the conductivity of a sample that you have. Thankfully, you're able to do a lot of these things on the cheap and by yourself by using something like this. This is a Node MCU V3 microchip programmable board that you will be using in this course, of course, as part of Open Lab number 3. But before you can, go ahead and start playing around with this and connecting things and sensing all these things, you kind of have to get a general understanding of electronics in order to proceed. Now, this is by no means an in-depth sort of tutorial on electronics. I just kind of want to get you all up to speed with certain concepts and words that you will be hearing a lot when you're looking at your various different sensors or you're dealing with your chip. We'll have a separate video on how to get using these things and how to deal with all the different parts, the software side of things, etc., etc. But before we get into that, I do want to briefly just talk about some concepts. And so this is what this video is going to be about. You are a scientist, and a lot of what you do as a scientist is measure things, the properties of things. Especially within physical chemistry, this is a very common process. Now, oftentimes, let's say you want to measure the surface of something, you would use an atomic force microscope, like this one shown here. However, those are expensive and hard to come by, and with the pandemic looming all over us, we don't necessarily have easy access to these tools. Similarly, let's say we want to take a TA spectra, a transient absorption spectrum, of some sort of a dye as you pump it with a laser and see what happens when all this excess energy gets put into it. Now, normally we go into the lab or go towards a facility that has one of these components and utilize it, but unfortunately we probably don't have one of these things lying around in our living rooms. And because of that, oftentimes we have to be creative with what we have. And so in order to be able to use these programmable microcontroller boards to do things that you want in order to measure a certain property of something that you're interested in, you kind of have to, again, understand the basics of a few key electronic principles. So we're going to go over that quickly and just get you kind of thinking and understanding some words that you'll be seeing as you're working with these tools. Now, this will be the first video in a series of small informative videos that'll help you get up to snuff with all these tools that you'll be given in your little goodie bag of electronics. This video itself is just going to focus on some analog electronics and terms like that. The next video will get you up and running with the Arduino IDE, so you're able to program and utilize your little chipset that you've been given. And lastly, you'll have a little video describing of all the different sensors that you've got, like this guy here, or this guy here, or even this behemoth-looking thing over here. Now, those will be all available for you to look through, and of course, if you have any questions along the process, you're welcome to reach out to me. We'll be having consultation hours as TAs, of course, so we can spend some more time discussing these things. Additionally, alongside these videos, you'll have access to a bunch of PDFs and documents that'll give you more information on these concepts, as well as all the details needed to use these little sensors that you're going to be given. As I was saying earlier, sometimes we don't have access to these fancy tools to measure certain properties that we're interested in. So we're going to be able to take this little board and add specific sensors, and of course be able to do that at home. While not as robustly or as high precision as we may need, it certainly gives us a good stepping stone into understanding how sensing works and how we can design our own tools to run our own experiments. In order to understand electricity, we have to understand what makes up electricity. And this, of course, are electrons, negatively charged subatomic particles that flow. Now, we can define current, or symbolically I, as the flow of electrons in a circuit. We use these electrons within the confines of a circuit to transfer potential and use devices to manipulate their flow to achieve a particular result. But as a budding electronics enthusiast, you should be able to think about current, or at least the flow of electrons. Analogous to the flow of water in a pipe, which we'll get into a little bit later, we can draw a lot of parallels between water flow and electron flow. Current is defined as the quantity of electrons passing a given point, and we use amperes as a unit of measurement to quantize this value. We should know that 1 ampere is approximately equivalent to 6.3 times 10 to the 18 electrons per second at a certain point. We always measure current at a point. Now, we should also know that in terms of SI units, 1 ampere is equal to 1 coulomb per second. And we know that each electron has 1 unit of elementary charge, or equivalently 1.602 times 10 to the negative 19 coulombs. Now, this is important to note because you're going to be seeing the use of ampere and currents quite a bit. You might find that this device requires a specific current, let's say 20 milliamps, in order to work properly. So you're going to have to be able to set up your circuit to provide this particular sensor that adequate amount of current in order to work. You'll see how current ties in with other concepts such as voltage and resistance in just a moment. Back in the day when current was first discovered, we of course did not know that electrons were negatively charged. That was a couple years later when J.J. Rutherford discovered the electron. So at the time, Benjamin Franklin thought these were positively charged particles and that current flew from a positive source to a negative sink, as if they were positive particles. But in reality, we know that electrons are negative and they'll flow from a negative source to a positive sink. And so, because electrons are negatively charged, we consider flow from a negative source to a positive sink as electron current. Now, this is more scientifically correct as to what's going on, but unfortunately for us, a lot of electricians like to use conventional current, or the flow of positive particles, which is the opposite case. So we are going to use conventional current throughout this course, and we're going to assume that the flow of electrons is from a positive source to a negative sink. Now, you and I both know that's not true, but unfortunately that is convention, and that is what we have to deal with. So just to show you that schematically, we can see in the top left diagram the conventional current, that electrons are flowing from the positive terminal to the negative terminal of our voltage source. Unfortunately, that's not true, but that's unfortunately how conventional current is used these days. Electron current, which is much more scientifically accurate as you can imagine, has electron current flowing from the negative terminal to our positive terminal of our voltage source. Now this is important to know, but not critical. Just understand that there are two different ways of describing current. Voltage. This is another term you've likely heard before. Voltage uses the symbol V, and it is defined as the electric pressure or force applied across two certain points. We can only measure voltage across 2 points. We can't actually measure voltage at a singular point. Of course, we measure this in volts, and in terms of SI units, 1 volt is equivalent to 1 joule per coulomb. And we can kind of think of it as the work that's required to push electrons through our circuit. More formally, voltage is the work required to move a charge between 2 points at a different potential, and this is important. Again, we're always looking at 2 points relative to one another to understand voltage. Last but not least in our trinity of basic electronic terms and principles is resistance, which is given the symbol R. Now, resistance is defined colloquially as the obstruction of electrical current. The name sort of implies that there is a resistance, there's something to impede the flow of electrons. Now, in terms of the units, we measure resistance in ohms. So we have resistors, and they look something like this, small little rods. These are typically made of a metallic film, and they're designed to impede the flow of electrons. However, that excess energy has to be dissipated somewhere, which you should be very careful, because electrons, when they flow through this, they lose quite a bit of energy, and because of that, you generate a lot of heat in these resistors. Fortunately for us, we're dealing with very small resistors, and we don't have to worry about that so much, but just keep in mind that that excess energy has to go somewhere. And so resistors often work by mechanically constricting the flow of current, and again, that excess energy has to be dissipated somewhere. Let's say you pick up a resistor from your pocket and you look at it and you go, okay, I have no idea what value of resistance this has. Of course, that's pretty important when it comes to designing your circuit, but fortunately for us, we can just use the color codes directly on the resistor to determine what resistance they offer. And so when you look at the resistor, you'll see a series of stripes. This is called the color band system of identification, and here we have a fancy table. So let's throw up a fake resistor on the screen here. Now, looking from left to right, we see that we have a red band, followed by a black band, followed by a brown band, followed by a gold band. We always read from left to right. Our gold or silver are always going to be on the end, so we don't actually use that to determine the value. That tells us what the tolerance is. And so if we look at this resistor, we see that the red is 2, right? We're looking at red in the first band, it's 2. We're looking at the second band, which is now black. We see that in the second band, black means 0, which means now we have 20. The third band is our multiplier. So we have a multiplier of 10 ohms, which means that 20 times 10 ohms is 200 ohm. We know that this is a 200 ohm resistor, and the gold band at the very end tells us that this has a plus or minus 5% tolerance on that resistance. If you're very picky about the stability of certain electrical parameters in your circuit, you may want to make this as small as possible, but 5% is pretty excellent, and most of these things have some tolerances, so we don't have to worry about that. You can now use this handy little chart to identify the resistance of the resistors that you've been given in your package. Now, most of us don't have access to a multimeter all the time, which would be far easier, as you can just measure the resistance using that. But this is the more sort of traditional way of doing it. So to summarize these things that we were just talking about, we have three sort of core principles to focus on. Starting with voltage, or V as it's given symbolically, this is measured in volts, of course. This is defined as the electrical pressure or force, but more importantly, we have to measure voltage across two different points. There's no such thing as a voltage at a single point. Resistance, or which is given the symbol R, is measured in ohms. This is the slowing or the impedance of electrical current, usually mechanically through something like a resistor. Now, this is going to dissipate heat, and obviously there's going to be a voltage drop across this. And lastly, there's current, symbolically given the symbol I. Now, this is measured in amperes, and this is defined as the flow of charge or electrons. Remember that there are two types of definitions for current. There's conventional current, which is the flow of current going from a negative source to a positive sink, or actual honest-to-goodness electron current, which is the opposite. We're going from a negative point to a positive sink, as electrons should, because they're negatively charged particles. Interestingly enough, the entire sort of idea of an electrical circuit is very analogous to that of the flow of water. And so if you think about, again, a battery being a source for the water, right, a pump, we can think of our wires being our pipes. We can think of voltage as the pressure in the pipes. We can think of current as the flow of water in these pipes, and we can think of resistance as obstructions in the pipe, such as sand or maybe like a physical shrinking of the diameter. Now, these are important things to consider because these are sort of the terms and terminology that you're going to be seeing in a lot of documentation. Let's say you want to measure the intensity of light coming off of your computer monitor. Well, you can use a sensor like this, but in order to use this, you might have to wire up some resistors prior to connecting it to your actual sort of microcontroller, and that often involves you reading the documentation, understanding what voltage is required, what resistance is required, and what current is required in order to ultimately use one of these things. So before we get into understanding how to use this, we're going to have to understand this. Last but not least, we do want to talk about some key mathematical equations that are incredibly important in understanding the relationship between these three concepts. So let's begin with Ohm's law. Simply put, Ohm's law is the relationship between voltage, current, and resistance. And what's really important about that is that given some sort of simple circuit like this, where we have a voltage source on the left, a current flowing through the circuit, and some sort of resistor defined as R, if we know 2 out of 3 of these properties, we can calculate the third one no problem. Let's say for the sake of argument that we have a 9-volt source, a battery, and we have a 20 ohm resistor connected to that. Our circuit is simply that. It is a battery connected to a resistor. What is the current flowing through the circuit? Well, we have voltage and we have resistance, and now we can take Ohm's law and rearrange it to solve for the current. Now, of course, this is a very simple example, but we've taken Ohm's law, we've rearranged it so that its current is equal to voltage over resistance. We're using SI units. Of course, if they're kilovolts or kilo ohms, we have to drop the kilo and convert it to base units. And in our case, 9 volts of voltage divided by 20 ohms of resistance implies that there is 0.45 amps of current flowing through the circuit. Two other very important concepts are Kirchhoff's laws of current and voltage. Now, symbolically, this is what they look like. Let's begin with Kirchhoff's law of current. Now, given that current coming into a node, and just to explain what a node is simply an electrical junction, or a breaking point in the circuit. All current coming in must equal all current going out. So let's say for the sake of argument that the current at I1, I2, and I3 are 2 amps, which means that we're getting a total of 6 amps entering the node. Now, that means the current leaving must be 3 amps at I5 and I4. Otherwise, their sums wouldn't equal to 0. So this is a very simple law and just allows you to understand how current flows, or how the conservation of current works, especially at nodes where it's the most important. Last but not least, we have to talk about Kirchhoff's law of voltage. And what that means is that the voltage drop, or the loss of potential over components in a circuit, must all equal to 0. So in this case, we have a battery denoted at start, and we have 4 resistors of the same resistance. We know that there's going to be a voltage drop across all of those, and we know that the voltage drop, or the sum of the voltage drop across all of them, is going to equal to 0. And that's important because by the time we circulate across the circuit, we should lose all of our potential. Last but not least, we have to think about how to calculate resistances if we have multiple resistors. Now, in the case of parallel resistors, where 2 resistors are split by a node, we can use the following equation, where the equivalent resistance, or the inverse of the equivalent resistance, is equal to the inverse of both resistances summed. So we'd sum them together as their inverse form, and then take the overall inverse to get our equivalent resistance for a parallel set of resistors. For a series set of resistors, this is far more straightforward. we have two resistors in a line. There's no node separating them, so all we have to do is simply sum the total resistances. Now this applies to circuits that have more than just two resistors. We just simply keep summing, in the case of a series resistor, all the different resistances, or in the case of a parallel resistor, all of the different inverse resistances before we take the overall inverse. Now, if you're still having trouble with some of these concepts and some of these mathematical terms, like as I mentioned, there is a document available for you to look through to just sort of spend more time familiarizing yourself with these things. And of course, if you're still having any difficulties, you're welcome to just send me an email or drop by my office hours and we can talk about all these concepts all we want. Well, time permitting, of course. So with that aside, up next will be the process of familiarizing yourself with this little guy here, the Node MCU V3. This is going to be your microcontroller board that you're going to be using to use all these sensors that you've been given, as well as how to use the Arduino IDE, and of course, using digital sensors, how to get libraries for these, how to use them, and some ideas of how to use them themselves. So thanks for being patient and listening in today. Again, if you have any questions, feel free to reach out to me, and have a fantastic time learning how to get neck deep in electronics.